Well, we're going to start out today with just the topic that I was asked a question about, and that is, how do you come up with derivatives the hard way? One of the questions I was asked, actually two of the questions, tie in with the definition of a derivative, the derivation of a derivative through the definition, and then we'll get back to the rules of derivatives, which are really just memorization facts that you can apply time after time to come up with whatever answer you need. So the first question was really about a theorem in the book. So let me point out what that says. It's a good question because I did skip it here in this class. This is so-called theorem 3.6. What it has to do with is, what is the derivative fundamentally? And in terms of algebra, this is the picture that we've looked at. Okay, and perhaps in terms of pictures, you'd have some curve over here. You'd pick a point with coordinates A and, in this case, f of A. We'll assume this is a function y equals f of x. And what we'd like to do is find out what the slope of the tangent is to that particular point on the curve. And what we've done in the past, let me briefly go through that, just review, is pick a second point Q on the curve, look at the secant line through those 2 points, big blue one here, and what I've been doing up until now is said, well, we'll come over here h units. That's a little bit farther than my x-axis, so let's continue that out. We'll come over here h units to a plus h, so that the coordinates for q would be a plus h, f of a plus h, since it is on the curve. And then when we compute rise over run, the run is simply h units going from a to a plus h. That was the run. The rise is the difference in the y coordinates from f of a to f of a plus h. So rise over run, the slope of the blue line, is exactly what you see up here inside the limit sign. And the picture we've seen several times in class, once by computer animation, is that as q moves into the p position, blue line moves into the orange line position. The slope of the secant line, which is what we have here, this fraction, becomes in the limit the slope of the tangent line. Okay, you've seen that picture. Now, the only thing that's different in the so-called theorem that's in the book there, 3.7, is they prefer to write this as follows. Let's write it as the limit as x approaches a, f of x minus f of a over x minus a. It looks different algebraically, but it really is the same thing, because rather than call this a plus h, we're going to call it x. So the difference in x coordinates is x minus a as opposed to h, and the difference in the y coordinates would be, since we're at x, f of x, q's y coordinate, minus f of a. That's the same. So now the rise over the run is what you see in yellow, f of x minus f of a divided by x minus a. That's all there is to the so-called proof of the theorem. It's just another statement as to what you want the variable point x coordinate to be represented by. Now, some of your problems are a little bit easier to do in perhaps one form or the other. I can't say that you should always do one problem this way and another problem this way. I'm not sure if I could decide even beforehand which is the easier way. But they do ask you in some problems to make your derivations according to this rule over here. Question?
Yeah, the problems that they asked to do were 17 and 19 on page 98, and I had problems with both of them.
Okay, let's take a look at one of those problems. 17 or 19? Let's take 17. They look about the same. I think there f of x is, what, 6 over x squared? Okay. So they're asking you to use this second formulation. That would ask us, well, do they have a specific point, or is it not even mentioned? Okay, let's use exactly what we have up here. What I'd like is f prime of a. That should be the limit as x goes to a. F of x, 6 over x squared, minus f at a, all over x minus a. Okay? We're using this formulation up here. It's f at x minus f at a over x minus a. No, this will be f prime at a. Did I have x back here? No, this is a also. You see, we're holding a fixed. I'm going back to the book's notation. And either calling the variable point's x-coordinate a plus h in our original definition that I've been working with, or just call it x. So that's the variable point now. Okay. You had problems? Anybody have any suggestions on what we should do next? Or is there any problem at all with this thing as a limit? There always is. It turns out for derivatives, you're always going to take a run that goes to 0 and divide it into a rise that's going to go to 0. You're always going to get a 0 over 0. So you've got to do something fancy in order to get this thing into another form that you can work with. Okay? Someone suggests conjugate. That's pretty much a radical sign problem or a root problem, maybe even a cube root problem. I'm not well, I can guess what the radical would be, but I'm not sure it would take care of what we need. Anyone else?
Common denominator.
Common denominator up in the numerator here. I think we've done this once or twice before. So let's try it again. This would be the limit. And you have to be careful with your fractions as usual. Big bar for the overall fraction, the one on top, is going to be 6a squared minus 6x squared all over x squared a squared. Okay. You can factor out a 6 for sure. Right, difference of two squares up there as well. So you've got an a minus x and an a plus x. And the way that I have the fraction right here, I could rewrite it maybe with just one bar, let's say. X squared, a squared, and also an x minus a. So I've just taken this fraction and put this in the denominator, in effect, to get this result here.
So
Question?
the x minus a in the very denominator,
Yeah.
you just revert right up to the next denominator?
Yeah, it's the way it works. I don't know how many ways I could write it to make it. Another way to say is, well, I take that thing in the denominator and write it as a fraction, maybe. Okay, so that would in effect take care of that bar problem that you see. I'm not sure I can write it any way that's really appealing to everybody all at once. But anyway, we finally get this cancellation. Well, that's the negative of this. But anyway, we got rid of the bad fellow, so to speak, in the denominator because we were letting x approach a. What you're left with is really a rational function in variable x. It really is a polynomial in x, numerator and denominator. So I'm saying it's okay now to plug in x equals a, numerator and denominator. So you'll get a 6 times 2a on top. Right, a negative. Thank you for reminding me. And on the bottom, when we plug in x for a, we get an a squared times a squared, or a to the 4th. So it looks like to me we get a minus 12 over a cubed as our answer. So that was the derivative of f of x if it were 6 over x squared. This is a so-called long way. And of course, we expect you to be able to do this for some, I won't say easy functions, but they're not all that terribly complicated either. And of course, what it requires is a trick. Now, what we're hoping to do here shortly is avoid such a trick. And that is to look at this function and say, hey, this is just a constant times a power of x. So there's this rule which says, first, derivative of a constant times a function is the constant times the derivative of a function. And as a power of x, that would be a minus 2x to the minus 3. So we get a minus 12 over x cubed, and by George, that's exactly what we had, except we plugged in a for x before. Mr. Bond?
Where did that negative 1 come from again?
Because I had an a minus x versus an x minus a in the denominator.
Oh.
So, by the way, we notice that indeed it does pop out here using our differentiation rule as well. So, it checks, is what I'm saying. So if you are not too convinced about the power rule, I guess I've just tried to convince you that one more case, indeed it does exactly what it's supposed to do, but much more quickly. You just have to memorize some stuff to be able to come up with these now. No tricks here. You just literally write down some rules.
And the test, you'll want us to do it the long way, but you're saying it'll be beneficial to know the other rules so we can just check them.
Okay, this I think is what makes, at least my viewpoint, college math different from high school math. Your teacher would hope you would know all of these rules. I would hope to know how you got them and perhaps what do they mean in terms of some pictures or applications. So in terms of applications, that's another question that's going to come up. Maybe I've satisfied your question about what to do. See what you can do on 19. It's somewhat the same. But the other question that was asked was on page 92 as to what good is differentials, or derivatives, I should say. What you're supposed to do there on page 92, number 5, is take a distance function, which is a simple polynomial, 4t squared plus 3t, and write down the velocity. So this tells you what the position is for a particle, and we'd like to find out where it's going, what direction it's going and at what speed. Here's the picture, I guess. Here's the origin. And in fact, for this particular function, we start at t equals 0 at the origin. At t equals 1, we're at 7 units, etc. And in a sense, some continuous sense, we get from that point to the other. But it's not uniform motion by any means. This particle is not moving at a constant velocity. We're, in fact, interested in just whether or not it does speed up, or maybe it backs up, maybe it goes to the left, and then starts off to the right again. So the emphasis is not on the picture of the final result. The path is eventually to go from here to here, but just what motions did you go through to get from there to there. It's like watching the America's Cup race. It's not the finish so much, but how they got there. So what we're after is this velocity. I claimed it was f prime of t. We've seen some examples in class y. This problem is trying to point out y in more specific detail. Well, part A of the problem is to find the average velocity from, well, at t equals 1 to t equals 1.2. First part, find average velocity. That means over a nice fat time interval, you're supposed to take distance, the net distance you've traveled divided by the net time of travel. Now, distance here will be interpreted as difference in position. That is, if you back up your car, the speedometer won't register that you've actually traveled anywhere. If you start at a point, back up and go back to the original point, as far as we're concerned, you didn't go anywhere over that time interval. Okay. What we have to do then is say, well, gee, that's your final position minus your initial position divided by the time you traveled. Well, that looks familiar. That's close to being exactly what we've been talking about up here. That is, rise over run can be talked in terms of distance over time of travel. And as I said, if you're an econ major, you can talk about change in cost per change in items produced, rate of change of cost per production, let's say, or whatever your interest is. So very often you look at these fractions to see what the average such and such is. Now in this particular case, it's a matter of plugging in. In fact, I would prefer not to do it. We did it in the other section. I believe I got someone to agree that it was 11.4. I'll just leave the computations to you. It's a matter of putting the numbers in and working it out. And I think if we did it from t equals 1 to t equals 1.2, pardon me, 1.1, I think the average velocity, let's call it v sub a vg, was 11 point, wish I could remember what it was supposed to be. I can't remember, so I shouldn't write it down. I was trying to show you what the pattern is without actually having to go through the computations. I'll come back and fill it in a second because I want to show you what this has to do with instantaneous velocity, and when I do that I'll find a nice little formula I can use. What I want to do is avoid this calculation every time. So let's come back here and go on to the next part of the problem, and I'll come back and fill that in. At least the next important part of the problem is to find the instantaneous velocity. I just said that that was the first derivative at, well, let's do it at a fixed point A, as we've been doing it here already. This, by my first definition, is this expression. You see, we're talking about taking a fixed point A and looking at an average velocity over a time interval length h, and then letting h shrink to 0. So the effect is that in the limit you get your speedometer reading. Not the average over an interval, but the actual instantaneous speedometer reading. With a plus or minus sign, which you don't usually get in a car. You know, it tells you whether you're going forward or backwards, I guess, is what we're talking about. Now this problem is, I guess, relatively easy compared to the ones we just talked about. And that is, our function is just a polynomial. So if we plug in 4a plus h for f, there is f at a plus h. Here's f at a. And we're supposed to divide all that by h. Okay, well, let's see how much algebra we can get through. If we expand this out, we'll get 4a squared plus 8ah plus 4h squared. Out of here, we get 3a and a 3h. Out of here, 4a squared negative, also negative 3a. I've said before, and I hope it's still true, if it doesn't have an h in it, it's going to have to cancel. Otherwise, I've made a mistake somewhere. So those two terms disappear altogether. And what we're left with is the limit of that expression over h. I'll cancel the h, which is now freed up out of every term, 8a plus 4h plus 3. Okay, a little bit of algebra there. And then when h goes to 0, I'm talking about a polynomial in h, so I can just plug in there, and we get an 8a plus 3 over here. So there is your velocity function. That's v at a, is 8a plus 3. And as I said, the velocity of this thing, the speedometer reading, is not uniform. It's not a constant velocity. As time goes on, which is t here, if I were to replace a with a t, as time goes on, you actually, in fact, pick up velocity. So getting ahead of the problem a bit, that is the actual speedometer reading, plus or minus sign thrown in for free at any instant. Now, why I went on into this problem is that right here, before I took the limit, is the average velocity that I was trying to compute earlier. So in particular, if t a equals 1, at time t equals 1, you've got 8 plus 3, which is 11, plus 4h. Okay? So the average velocity is, in this case back here, 8 plus 3, or 11, plus 4h. And that's why I didn't want to do it. I didn't want to have to go through this fraction every time, because there's a great deal of simplification in the general form. And now when I talk about going from 1 to 1.1, h in this case is 0.1. So there is, in fact, 11.4. I must have made a mistake in the earlier one. If h is equal to 0.2, then I should have had not this, but 11.8. I suppose that's why. My memory wasn't working too well either. And if h is 0.01, it's 11 plus 0.04. So you can see the limiting process getting close to 11 as your interval shrinks. But of course, we've done that most arbitrarily over here, and at t equals 1, in fact, you have a velocity of exactly 11. Question?
Where did you get the figure for the time on that?
Well, the question was, where did this come from? I think this was part of the problem. I think part A, they said, well, give us the average velocity over these time intervals. So they picked 1 and picked also a varying final time. And these final times are getting closer and closer to 1. So the average velocities you were supposed to see, if I'd kept on going here, were getting closer and closer to 11. That's supposed to make you a believer that when you get all done and you look at this velocity function, indeed it is 11. But better than that, we've got the velocity for any point in time whatsoever. We don't have to go through those limiting computations. And before I answer the next question, even better than going through all this work over here, if one knows the rules for polynomials, you know that it's 8t plus 3 just looking at this thing. So that's what makes calculus neat, is if you know the rules, you've got instantaneous applications about instantaneous rates of change, as it turns out. Question?
So what was your reasoning for bringing back the plus 4h, sir?
Oh, well, I'm just lazy. I don't have a calculator. And I didn't want to go through the arithmetic to produce, I think it's 4 or 5 average velocities that they ask you for. I'm just saying, if you're smart, you'll know that in the instantaneous velocity computation, when you simplify, before you take the limit, this is the average velocity starting at any time a, extending h units. So all those problems over there I can just plug right in here. A equals 1. We're starting at 1 unit. So now it's 11 plus 4h. So the easy way to do this problem is to simply plug in various values for h. As they get smaller, it's very obvious that it's getting close to 11. It's not so obvious when you do the arithmetic up here. Do you see what I'm saying? Is that I'm supposed to take 1.2, square it, multiply it by 4, add 3 times 1.2, and then from all of that subtract 4 times 1 squared, and also 3 times 1. And then you do all that arithmetic, you should get 11.8. Well, rather than do that 4 or 5 times, I think it's nice to put it in this form. I think maybe I've covered everything that was of interest. I guess there are a couple of questions which are easy in this case. When is the object moving in the positive direction? That's whenever the velocity is positive. A positive velocity means a positive rate of change of x. The way I've drawn things, it goes to the right. If the velocity is negative, the rate of change of x is negative with respect to time. So things are moving to the left. And since it's a linear function, it's positive, obviously, when t is greater than minus 3/8. And you can answer that question quite easily. That's why we've talked about inequalities in class, because you're interested in certain things like change in velocity. When is it positive? When is it negative? So it kind of brings us back to some old haunting review type problems. Okay, I think that was a set of questions we initially had. Maybe we could now get into something a little bit different, but not altogether. We talked about rules of differentiation, and every so often, as you've, I hope, noticed, I've applied those rules to show you that they indeed are very nice shortcuts to get you to the answer that you want. And for the most part, the hard types of problems that you run across, up to this point anyway, would be, say, rational functions in x, where we'll take a polynomial and divide it by a polynomial. That's probably about as hard as it is, and it would require a quotient rule. We've talked a little bit about the quotient rule. I'll talk a little bit about it some more, but what I'd like to do is get into the next section and talk about a whole different class of functions, not just powers of x or sums and products and quotients of them, but things that actually come up in the real world also. And I'll give you as an example, in fact, you'll run across this in your differential equations course. You take a spring with a very good mass, heavy weight on it, and assume the spring is near perfect, and you pull it down and you let it go. And if there's negligible friction, the thing will bob back and forth. And if you had really a needle on the thing, what you would see is a sine curve being drawn out. Now the question is, now that you see there's a trigonometric involvement there, what is the velocity of this so-called pendulum or oscillation? What's the velocity at any instant in its oscillation? So we're still talking about straight line motion, as we have been here in class, up and down now. But now it's not just polynomial, it's much more challenging, let's say. It's sinusoidal. Okay, so the question is, seeing maybe there is a potential for application, how do we take our definitions here and apply them to the trigonometric functions? Okay, so what I'm saying is, and I'm going to redraw a picture, but it's not the general one I had. What if I take a sine function, about like that, roughly. Let's say I pick a point on it. You know, it's really the same picture I just had up here almost. Draw the tangent line to it, and ask the question is, well, if this is A, what's the slope at that particular point on the curve? Now, some of you know the answer, and it's surprising. Still is to me. I've seen it every year now. If you start out with the sine function, it turns out that the slope is just the cosine. Well, since I'm at A, I should put that in there. The slope at the point when x equals A on the sine curve is the cosine of A. Kind of surprising, actually. And when you talk about the beauty of nature, most people think of trees and flowers and things. Well, we mathematicians get kind of excited when the sine and the cosine get so intimately tied up. Well, that's another subject altogether. What I did want to get into, though, is the kind of notation you'll see in your book. They'll say the x derivative of sine x is the cosine, and the x derivative of cosine, and this is something you have to worry about, you've got to remember that negative, and it turns out to be the negative of sine. So it's not as beautiful as it could be, but it's close enough for me anyway. So those are the two rules that we want to toss at you today, and actually show you that this is indeed true. So let me go through the process. Notice that the rules of differentiation that I've trotted out before are not at all applicable. You do not see any powers of x. So when someone says, do we have to know the definition of the derivative, the answer is yeah. Lots of times you're going to come up with a brand new function, and you're going to have to trot through that definition one more time as best you can to come up with a result. So in this case, y is sine x. That's our f of x. And what we would like to find is, say, f prime at A, which would be, let's use the original definition, f at A plus h minus f of A all over h. No matter what the application is, it's the same old definition. Bobbing springs, electrical circuits, whatever. Well, let's see. It's going to be a little crowded, so let's move it over. This will be the limit of sine of A plus h minus sine A all over h. Let me let you stare at that for a couple of seconds. Okay, up till now, like the problem we had on the board earlier, the whole trick was to somehow cancel the h with the h. I'm not really indicating that's what you should do here. Of course, the problems were difficult because you had to discover some great little trick, conjugates, common denominators, those kinds of things in order to make stuff disappear, and out pops an h and cancel and go on your merry way. However, I'm just telling you right now, the sine function is so complicated, it's not that simple. H will not just pop out by itself. And so we're going to have to use new tricks. And I'm just asking out of curiosity, I suppose. Anyone see what kind of trick you might first apply?
How about that one theorem we have where sine of h divided by h equals 1?
Obviously, or maybe not so obviously, but that's why we spent so much time on sine h over h. It turns up right here in this particular part of the problem. I hope I warned you at that point that when we did that limit, in fact, we were finding what the derivative of sine is. And so that will be a key step in this process. But notice I don't really have sine h over h. I got sine of a plus h over h. Okay, someone says multiplied out. I think what you really want to say is use a trigonometric formula, which will in effect pull it out. Now this is not an obvious trick. If you haven't seen it, you'll see it. And if you can see it on your own, I congratulate you. It's not that obvious. So let's come over here and rewrite that first sine of a plus h according to one of the trig rules, which is sine of the first cosine of the second plus cosine of the first sine of the second. So that's sine of a plus h right there. We were supposed to subtract sine of a and then divide by h. And as someone noticed, right there is just the critter we've been staring at for a day or so, not so long ago, sine h over h. So what I'm going to do next is a rather obvious step, and that is break it up into some pieces. Let's pull that one out, in fact. Make this limit as h goes to 0. That would give us cosine a sine h over h. And what we're left with is sine a cosine h, another sine a. And that kind of screams to me, factor me. So I will. And by putting things in the right place at the right time, what do you know? There's that other formula we investigated. And now the process is the limit of the sum is the sum of limits, et cetera, et cetera. And so we get cosine a times 1 plus sine a times 0. So nothing out of that term. And by George, there you have it, just as I had said. If you take the sine function at x equals a, the tangent will have slope cosine a. And over here, see? I predicted it. It's amazing, isn't it? And, of course, that gives you, because a is general, this relationship right here. Derivative of the sine is the cosine. Okay, was there a question? Someone looked like they were ready to ask a question. Yes?
I don't understand where you got, I can see where you got cosine A over sine h over h.
Okay, that was just one of the terms, which I,
Right.
see, I'm looking at this as 3 fractions. I pulled this one out,
Right.
and the other two I didn't really want to break up. I want to squash them together and factor the sine A out. So you get a sine A cosine